we have understood that charges can be distributed in a different manner, that is, in a continuous manner. Now, we will start off by deriving one of the most simplest form of this continuous distribution, that is, a charges distributed across a infinitely long straight line. We are trying to figure out the electrical field using Coulomb's law. So the derivation starts off in this manner. First, we're considering an infinitely long charge with a uniform line charge density. What does the word uniform mean? Like uniform as in you wear uniform to school. Uniform means, yes, evenly spread out. So we have evenly spread out charge whose density is given by lambda. We need to consider a point P, and this is where we are trying to figure out the electrical field. This OP is the shortest distance from this line to the point P, and let A be the distance between OP. This is your dq, a small charge. We are trying to figure out, or we have represented over here, dq's electrical field dE. And the length from, say, point A to P is L. And the distance from O to A, or length of OA, is Y. Agree? Now, let's express dq in terms of lambda. So what will that be? If I consider this length as dy into density, length into density will give us the charge in this space. Simple as that. I hope you guys remember the formula. Density is equal to charge by length. Now, if I want to find the charge, which we are trying to over here, I have to multiply density and length. As simple as that. And the length over here is a small length. Remember, this is the length. And that's your charge density. Right? I hope this is clear. Again, we have an infinitely long wire. We are trying to figure out the electrical field at point P because of this length. First, we're going to start off with a small charge dq and the electrical field produced by that. Right? So, another perspective. I hope this is big enough. Yeah. So, we have the dq over here, and this is the electrical field produced by that. And over here, we are trying to figure out the sum of all of this electrical field, right? The sum of all of this. Remember, this is infinitely long. So I'm able to show you guys sum of it. Sum of the lengths and their respective electrical field. So we are trying to take the sum of all of this arrows, which are infinite in number. How is that we're going to do that? Yes, using our integration. Now, before I start off with integration, a quick question. When I move across the slider, what is changing and what is fixed? If you guys answer this, you pretty much can do any derivation in this syllabus. Recognition of what is fixed and what is changing is very important in such derivations. So what is fixed and what is changing? So let's start off by looking at what is changing. So we have dE, that's clearly changing. Then we have the position of A, so basically Y is changing, L is changing. Agree? And what is fixed? A is fixed. Is it not? Whatever I do, distance from O to P is not changing. That is fixed. Right? And what else is changing? One more thing over here. I don't know if you guys noticed it. The angle is changing. Can you see that? Angle between this horizontal line and DE. So let me name this So this is your theta, and I'm calling here the same thing. So vertically opposite angle. So this is also changing. Now, the entire funda, I have mentioned it in the previous video. In this entire set of derivation is to find out what is fixed, what is changing, and express whatever is changing, express in terms of a single variable so that we can integrate. So we can take help of things which are constant, right? And we need to express y, l, theta in terms of one variable. And we have to make use of a and everything, okay? Right? So let's start off by looking at how a single of dq affects a unit charge kept over there. So we'll draw a free body diagram of a point charge at P. Now, so let's draw the free body diagram. So this is your dE, and that's your horizontal line, and this is your theta. Agree? So what do you guys generally do? We resolve. We resolve. So this is dE sin theta or cos theta. Correct, cos theta, and this will be dE sin theta. This is a parallel component or perpendicular. You guys can call it depending on whatever you want. So this I'll call it as perpendicular, or this is parallel, correct? Parallel to the wire. Sorry, perpendicular to the wire. And this is parallel to wire. This is going to help us. Now, let me do one more thing. Let me draw feed body diagram of a point charge at P itself. But here the catch is, continue this way itself, because of two components which are equidistant on, I'll explain what is this, but on opposite side of OP. Okay, let me explain that. See, here I have a component almost close to 4, right? This is OP, and OP is your horizontal line, and from OP, above the OP we have a point around 4, right? Now, exactly at the opposite to OP, we have another point in this manner. This is also close to 4. So whichever point I speak of, like say in this case, I'm talking of minus 6.4 below OP. I do have a component plus 6.4 above OP, is it not? Right? For every component like plus 1.1.43, I'll have minus 1.43. Okay, you guys can, I'm not able to fix it, but yeah, you guys got the funda. So every component which is above the line, right, I have a point below the line as well. How does this help? I'll show it. So again, we are drawing the free body diagram. So we have two components, electrical field, and resolve to two components. So this is horizontal, this is vertical. So when resolved, this is theta, this also will be theta. it would be in this manner. Agree? So this would be your dE sine theta, and this is also dE sine theta. What will happen to dE sine theta components? Yes, they will cancel each other. And this would be dE cos theta plus dE cos theta. This will add up. So basically the parallel components will cancel each other and the perpendicular components will be adding up. So the electrical field at point A, it's because of what? It's because of the perpendicular component. Agree? So clearly the parallel component will cancel each other. So our derivation became much easier. While the perpendicular components add up. Thus, our resulting field, that is the electrical field, is summation of perpendicular component. That is mathematically E will be equal to the, is it perpendicular component? Yeah. Sum of perpendicular component or equal to perpendicular component. Basically sum of all the perpendicular component. So this is nothing but cos theta into dE. Now, if I expand dE, we do it in the next line. Cos theta will be there. This will be dQ by 4 pi epsilon naught. And the length is, what is the length? From here till here, it is L. L square. Okay, guys. So please understand that I didn't take dE cos theta plus dE cos theta. That is 2 dE cos theta. I didn't take that. I just took one of it. This is because of 1 dy, right? Only this, only dq, sorry, this dq. This is 1 dq, not dy, dq. Right, at one end. Now, this is, okay, that's good enough. But can we integrate this? We have L that is changing, theta that is changing, 4 pi epsilon naught is constant, right? And the direction and everything, okay, direction is not changing because everything is in one direction. So this is good. But the problem here is how will we integrate this? This is where our panda comes. This is where our smartness comes. What is this? Expressing all the terms in terms of one thing which is fixed. Sorry, not fixed, but one thing that is fixed and not only fixed and one thing that is changing. So basically, it's convenient to express in terms of theta. For me at least. You guys can do it at any other variable. So I'm going to express all terms in terms of theta and A. First, I'll start with L. Right? Length L. What can we do? Well, it's quite simple. We have a right angle triangle. This is hypotenuse. A is your adjacent side. So what do we have? I hope I'm right about this. A by, yeah, adjacent is that. This is so, and cos theta. So we're trying to get an expression for L. So L will be equal to A by cos theta. Right? Next. So what else we have? we have actually dq also we need to express. So we need to express dq also. dq we already know it's nothing but lambda dy, right? Okay, let me do step by step. Next is dq. dq we know that it's lambda dy. dy is your length, lambda is constant. So now we have to express dy. Okay, so how will we do that? Well, let's go back to the figure. We have y, we have a, and we have theta. Again, yes, we're going to make use of trigonometry. Opposite by adjacent is tan theta. So y by a from figure, y by a is equal to tan of theta, right? So y is equal to a tan theta, but we want dy. So we will differentiate with respect to theta. So dy by d theta is equal to a is a constant. So this is secant square theta. Therefore, dq will be equal to lambda a times of secant square theta d theta. Make sense? And finally, limits. See, we need to add, but from where to where we should add? That's the question. Now, how will the limit change? So everything is in terms of a and theta. So a is fixed. So we need to understand theta. What value to what value are we adding? I'll give you guys some clue. Let me do it with this itself. So just a second. I thought it was just a second, guys. Oh yeah, it's here. Okay. Yeah. So I kind of got it close. You guys will understand why. Now you can see, look at the angle over here. Angle and the values are changing. Look at that. Remember, this is supposed to be infinitely long. I have a limited line. If I keep going, what will happen? If I keep going, what will happen? So that is now reducing to 0, and other end, this will be negative. Actually, all these are negative values. If I keep going, what will be the angles? What is the pattern? Look at the pattern. What is the pattern? So it is increasing. At this point it's 0, and it's increasing. Actually, it's negative, but anyways, negative value. It's increasing to, yes, minus 90. Other end, it will keep increasing to, correct, plus 90. So basically, right? So theta will vary from minus 90 degree to plus 90 degree. So you pretty much have all the things. Now substituting all the above in E. So E will be what? E will be equal to integration of minus 90 degree to plus 90 degree, and 1 by 4 pi epsilon naught, that will not change. And we have cos theta, if I remember right. And what else we have? We have L in the denominator, dq in the numerator. So dq is lambda a secant square theta d theta, and in the denominator we have L, that is a square, that's L square, right, divided by cos square theta. Now it's just a matter of simplifying it. So we have 1 by 4 pi epsilon naught lambda a, that is constant. Actually, a square and a will get cancelled. So we have a in the denominator. Integration of minus 90 to 90. We have this to be cos square, cos cube, secant square. So this will be cos theta d theta. Agree? So lambda by a 4 pi epsilon naught. Integration of cos theta is sine theta. And the limits will vary from minus 90 to plus 90. And when you substitute it, sine 90 is 1, sine minus 90 is minus 1. So this will be 2. So this is basically 2, guys. So 2 divided by 4, 1 by 2. So basically this is lambda by 2a pi epsilon naught. Right? So that's your electrical field at point P because of infinitely long straight charges that is lined infinitely long along a straight line. So let's have a look at give ourselves an overview. First thing is we need to draw and look at label them and look at what is constant and what is varying. So start off with free body diagram and see what will add and what will cancel each other. Once we understand what is going to add and what's going to cancel, all we have to do is express all terms in terms of fixed variables and one changing variable. So it's important to note that even limit have to be taken care of. And after this, it's a simple matter of integration. That's it. Okay, agree? So one last time. So you have an infinitely long wire. You are taking a point. We are trying to figure out the electrical field. So we are looking at so many electrical fields which are infinite number of, and they are varying in their strength also. Right? As you can see that they're varying in their strength. There are quite a few variables that are constant. There are quite a few variables that are fixed. Right? So these are fixed, while the theta, L, Y, D, E, all of this are varying. Agree? So I started off by looking at the free body diagram of a unit of a point charge of unit magnitude, unit point charge actually, at point P. Right? So we saw that the parallel and the perpendicular component, they are adding and cancelling each other. So whatever is cancelling, they are cancelling. Right? We can let that go. Whatever is adding, we need to integrate that. And to do that, we express all terms in terms of theta and a. This was a simple set of trigonometric functions. And by substituting and integrating, we got this particular expression. Right? So, this is just another way of remembering half lambda, the constant. I think this will help. For me, this is easy to remember. K is your 4 pi epsilon naught. And if I want 4 in the denominator, I have to multiply 2 in the numerator. So this will be 2. 2 lambda k times. That will be your another expression. Okay, guys. So now you guys have to pause, copy everything end to end.